Okay, so let me introduce you our last speaker. Andrzej is a software developer since 2004. He works mostly with C++ in commercial software, which includes safety-related and high-performance systems. He is a member of the C++ Standards Committee and a Boost developer. He is also a co-organizer of C++ user group Kraków. Known to the community for his blog on C++, akrzemi1.wordpress.com. Andrzej, in his speech, will appreciate coroutines, C++ coroutines in 30 minutes. Everyone, our final speaker, Andrzej. Andrzej, the stage is yours. Big applause.
Hi, everyone. Can you hear me well? Yeah, I think it is you who will appreciate coroutines in this 40 minutes. Thanks for attending this talk. This is the last one in this year's Code Dive, and you are getting yet another introduction to coroutines. Why this one rather than hundreds of others? In this one, you will not hear a word, hopefully, about defining those coroutine types, 20 customization points, and what magic functions get called. We'll not see, or almost not see, any of those. The goal is only to show you, to convince you why you would want to choose to use coroutines or to dive deeper into them. So it's more like a motivation or why they were added. And they were added to model the asynchronous computations primarily. So in this talk, we'll see how asynchronous computations work, why they are hard, and how coroutines make them even harder. No, just kidding. Actually, coroutines can help you there, make your code more readable, because you will be doing the asynchronous stuff, which is difficult by nature, and you'll be using common C++ idioms, regular code line by line, where you can use things like while loops, throwing exceptions, or doing RAII. Coroutines are difficult, but not because they could have been probably designed better, but they are okay. The problem with them is the thing they help you manage is difficult. That is, asynchronous computations are difficult. Only when you appreciate how difficult asynchronous computations are, you will appreciate coroutines. So the goal for the coroutines was not to, this is the way the languages are designed. We want to make simple tasks simple, but for complex tasks, we want to make them manageable, not too simple. We don't want to hide the complexity from you. We just want you to be able to manage it, the complexity. Coroutines, in this sense, are a bit like exceptions. It took me a number of years to understand and appreciate exceptions also, because again, they are the same. They are designed to handle complex things. So you may have been taught, I was taught like exceptions with examples like this one. You encounter a problem, you throw an exception, and you catch them in 3 lines. And it's like you don't you use exceptions this way. This is rubbish. You don't catch exceptions at the place where you throw them. Like you could have said that if I have a problem and I need to log it, I might as well just log it already and not use all this stuff. And you'll be right. This is how you do it, the short way. You only use exceptions when you are dealing with a complex system that you would otherwise find very difficult to manage. And the same is with coroutines. You will only appreciate them when you are dealing with a big system that does a lot of asynchronous computations. So let's have some theory about asynchronous computations. But first, let's start with the synchronous ones, because they are easier. Synchronous computations are all those that can be expressed in a control flow graph like this one. We probably all know it. The key characteristic here is that at each point, we know exactly what is going to happen next. There may be branches, but you always know that there is a branch, and you either take this one or that one, you know why. It is very predictable. You know what's going to happen next. And if this is not this, it is hell. Or not really, because another way of structuring a program, which people use and is actually more suitable for servers, is this event-driven flow, where we have a server, it does nothing, it waits until someone wants something from it. An event arrives, like you are sent a request. And then it has to do something, respond, process, give you a result, and go idle. And some other things occur, some other requests, okay, I'm doing something, and going idle. Some time elapses, I need to do some backup, I'm doing the backup, I'm going idle. Well, of course, it's not that that easy. Those requests will come all at once, hundreds of them, and you'll be doing all that stuff simultaneously, so there is going to be a mess. But conceptually, it's just server just responds to the events. And you don't know these events. You don't know when they will come, if they will come, how many. You just need to be prepared. Going back to linear flow, we know it pretty well. We know the idioms that work with it. We are used to it. Compiler vendors are used to it and give you good tools for visualizing your code, debugging. And well, the point is, yes, we are used to it. And the key characteristic, again, it's probably too obvious to even talk about it, but we'll say it anyway because we are doing it in contrast with asynchronous computations. You call our operation A needs to invoke some operation B. It calls the B and is blocked. Everything is blocked until the B is finished. And then we can move on to executing another operation. This is how synchronous operations work. And we also know how to handle different kinds of failures in this model. Like if any operation fails, the next one probably depends on it. And executing the next operation, C here probably doesn't make sense, may even be an error. So you don't want to do it, you skip it. Then if you skip it, probably the outer operation A failed because it didn't do part of the job. It's considered failed, and the next operation that depends on it needs to be skipped. And you just keep skipping, until you reach some point where this no longer makes sense. Like the server was not able to process user transaction, we just move on to the next one. I was criticized last time for saying this, because sometimes you have a better idea how to handle errors. That's true. So sometimes you do it in a different way. But this is a very good default. Most of the time, this is what you will do. If you don't know what to do, probably you need this. And this is what exceptions are for, actually, for canceling subsequent operations. If you don't use exceptions, you probably do the same manually with if statements. Also, for the linear sequential flow, we know pretty well, especially in C++, how to deal with resources. We tie them to the lifetime of automatic objects, and automatic objects represent a resource. When we call a function, we can use the same stack as we use for our instructions and function frames, and put all the data associated with the resource there. Then when we call subsequent functions inside our function A, the resource is there in the memory, we know where, in the stack. All those functions can use it. And when the last function that is using resources was finished, we know we can clean up the resource. This way we guarantee that every function that sees it lexically in the code has also access to it because it's still alive, and we also guarantee that it's destroyed as soon as no other function needs it. And then we're done. And all of this does not apply anymore when we are at the event-driven flow. We are actually familiar with the event-driven flow if anyone has programmed in C, and C++ inherits from C, so we get the interruption handling, the handling of the signals. This is a perfect example of asynchronous flow. If we want to be prepared for interruption, we will do these two things. We will define a callback function or handler or delegate, call it whatever you want. But there is a function, and we will tell the system that this function needs to be called in response to this signal. So we are making an association. This callback is not triggered now, it's not called now. It will be called later when the event occurs, maybe in a minute, maybe in an hour, maybe never. We just make an association of an event with a callback. And that's all there is to event-driven flow. Our diagrams, if we wanted to use them again, look different. The operation B is not invoked. We are just making an association. Operation B will be, if it's called asynchronously via this event association, may be called sometimes at some later point when the event occurs, maybe never. Conceptually, there is some connection between the point when we decided that it will be, that the association will be made, but it's not a temporal one. I mean, temporal in the sense that for sure it will be executed after we register it, but we know nothing else. And should this operation fail for some reason, there is no one to communicate this failure to. Operation C now doesn't care, doesn't know if B is invoked or when. It will never learn that operation B failed. So the communicating of errors will need a different channel. The only part that is synchronous is this act of associating an event with an operation. And if this fails, then we may consider skipping the other operations because it will interrupt definitely our asynchronous flow. And then this cancellation cascade can move on. Okay, so that's it for the introduction. Now let's do some asynchronous input-output, because this is where the fun begins. But first let's do the synchronous output, because it's simpler, at least in the code, but also conceptually. Assuming that we have a server, we have a framework that allows us to, so a set of libraries that allows us to write such code, because we will not be writing a server from scratch. At some point in our code, we will have this function session. We will be implementing an echo server. So whatever the client sends us, we send it back. Not particularly useful, but it's small enough to fit into slides, and it's a toy example that proves that something is actually working. So we'll create some buffer. Then we will call function read on the socket that will read the data from the client to our socket. The return type will tell us how many bytes were read. So we will shrink this buffer. So we create a smaller one with only meaningful bytes, and we'll write it back. And then we'll perform some logging. And that's it, very simple. If we run it, if we had the framework, it would probably work. But you don't want to write a server like this, especially if it needs to handle more than one session. Because this one, the first read we encounter, will just block it. We'll just block our server. So we are in a session. So the client requested a communication. They say they are ready to send us some data. So we are blocking on a read, but maybe they will send this data in a minute or in 2 minutes or tomorrow. We will be, and other clients are waiting. So we'll be just messing our server. So we won't do that. What we could do is to start a separate thread and run this session in a thread. And this would work because if this thread is blocked, other threads, if there are in the server, can be run in exchange or during that time. But you also don't want to do it. You don't just launch a thread in the middle of a running server, because it's an expensive operation. It will require allocating a lot of resources, a separate stack, and you will unnecessarily waste time, and it may fail. So what you usually do, you have a thread pool, and just grab a thread from a thread pool and tell the system or something that manages this pool to execute this function there. And it's a better idea, or it would probably work. but is also not an ideal when you are dealing with multiple threads. There will probably be operating system emulated threads, so the system will have to manage which thread is running right now. It will have to preempt one thread, launch another. This preempting will occur at random moments where you least expect it. So you will likely get into data races. You will have to protect with some critical section, mutexes. Then you may run into deadlock problems. And again, threads, sometimes you need to use them, but they may unnecessarily waste your resources. So an alternative that we could do that doesn't involve more than one thread is to use an asynchronous framework. So there will be a framework behind our back, which we don't have direct access to, that will be managing tasks that need to be done. And we will be just sending tasks to it, and it will be processing these tasks maybe concurrently, but possibly even in one thread. We'll do something like this. We will use this notion of event-driven flow. Our session now, when we call it, we'll make one call to our platform, or call it a framework. We'll just ask it to do a read for us at some point when the client is ready. We don't need to know about it. We'll just say that we are interested in data being read to our buffer and send it there and be gone. And make an association that when this read has finished successfully or not, call our callback. And in this callback, we will tell the system doesn't know what it calls, what's in the callback, but we will know that in this callback, we will make another call to the same system and ask it to perform a write. Not now, at some point, at some convenient point when it's ready to process this task, and when this write ends, call another callback that we will call log, and where we will do the logging. So we will cut this entire session into 3 halves. And the first of 3 halves is going to be a very short function. So when someone calls our session, it will be just making one association, so some small call to the framework, and then we're done. The remaining parts will be done at some later point that we cannot predict. And this all can be done even in one thread that shuffles all those tasks. So let's write it. Well, that's a nice implementation, actually. Yeah, this cannot possibly break anything, but let's fill some stuff in. First thing we do, we heap allocate the state of our session, of the session that only we know about, because we know what callbacks we will be calling. And because the function session alone is, as we said, this first block is a very short function, it will die, it will end immediately, the function parameters will be destroyed. We have to make sure that the socket, all data associated with the socket is saved somewhere safe. So we heap allocate. We heap allocate all the state, also the buffer, and we'll manage it through shared pointers. And next thing, assuming that we have a framework that allows us to do it, we ask it to perform an asynchronous read. And this doesn't read anything. This is just, so it has a different name than before. It is just a request to the framework saying that we are interested in data being read to our buffer at some point, convenient to the framework, convenient to the client. And when this succeeds or fails, but finishes, call our callback. So we're just making this association, and then we're gone. And then the server can move on to doing other stuff. One thing to note, that if we have such a library, And I'm not using its name, but implicitly, what I have in mind is Boostation library, because this is the one that I use in work. But there are probably others that do the same thing. When we have this socket, it serves two purposes. One, it is gives us an interface to the socket. Socket connects two ports on two machines, the client machine and our machine, and this is where we can manipulate with the bytes and with the transfer. But it also gives us access to the asynchronous framework, where we can actually make those associations of events with callbacks. This is also done via this socket object. And our callback that we will send, different interfaces is probably possible, and different libraries may choose to do it in a different way. But one good approach to the fact that the read may fail for a number of reasons is to give two things to the callback. First is this error code that will tell us if there was any error. And then we'll know that continuing with the session probably does not make sense. So we can check it, we can check what the problem was, and if there was no problem, if error code says that everything was fine, we know that the other argument, this integer, says how many bytes were read, as before. So we can try to implement it. There will be an if statement. We will be managing errors, handling errors via if statements. Now we cannot use exceptions anymore because we have spread our logic of our session across a number of callbacks. So the only thing we are left with is if statements. And under this if statement, if reading went fine, we can write the data back by shrinking the buffer, requesting that the write is performed at some time, not necessarily now, maybe later. And when this write is performed, call another callback, which is called done. And then we end. We don't wait until this callback is called or the write is performed. We just make an association. But it is possible that in the future the write has succeeded and then the callback is called, so we have to define it. It has a similar structure, the error code that tells if this went fine and the number of bytes written. But this time, if there was no error, we know how many bytes were written. Another if statement to check if there was an error, and if everything went fine, do the logging. And we can see two associations here. One for this on finished read, and the other is on finished write. And there is actually a third one implied, even though we cannot see it here. This entire function session is most likely a callback that we call in response to an event like on connection established. Because those asynchronous operations are viral. If you use them in a server, you probably use them everywhere. So the server will be a lot of those associations of events to callbacks at different levels. We can restructure our code if this is convenient or not. I'm not sure myself. So that now I define the bodies of the lambdas exactly where I pass them. So this may give you an impression of the order in which those operations are invoked. And probably the most important part here is how we deal with memory. We said that I needed to allocate it on a heap. I manage it through a shared pointer. And this may look easy, and you may not even notice that, but I paid a lot of attention to pass this shared pointer by value to every single callback that I use. This way, I make sure that the last one to touch the session turns off the lights. And it looks simple. This is also always the property of a code. If you do it right, if you you spend a lot of hours thinking about every corner case and you made the final code, it looks simple. But to achieve this simplicity, you had to go through a lot of trouble. And it's very easy to get wrong. But we have to do it without coroutines. There is no other way. And now I'm curious, well, because I've seen this example for weeks now, so I know more or less what it does. But how do you feel? Is this code manageable? Do you know what it does? Is it easy? Would it work for you? Who thinks it is bad? It's complicated. Yeah, the right answer. Huh? But the point is, I made it very simple. Because normal functions get more parameters. You have more things in a sequence. This code would be a way bigger if it was a real code. And doing the calling lambdas inside lambdas, it's like lambdas are cool, but when you need to use them, you always obfuscate the meaning of the code. So it works. People write asynchronous servers in C++ for years, but you cannot be fully satisfied with doing this because of the tricks that we have to do. One thing to note before we really go to the coroutines is that even though those things happen asynchronously, there is a sequence to it that is not violated, in the sense that we only perform a write when we know that the read has succeeded, and we only perform the log after the write has succeeded. So there is a sequence there. We are in control when we pass control to the system. It's not like the system preempts us. We control when this happens. And the calling session, the function session, is just a tiny bit of the function. The rest is in the callbacks. And we are telling two stories, actually. One story, the short one, is the one that the compiler sees, is the normal returns from the synchronous returns from the function. It's what the caller sees, what the compiler sees, what the debugger sees. The debugger will be able to help you with this part. But the more I think interesting part of this logic is this entire session that I know there is because I understand what I put in the callbacks, and you know what it is because I told you, but the compiler doesn't know what it is, or other tools. Like debugger will not be able to help you there. If you ever debugged an asynchronous program, good luck. You can see that you are in the middle of the operation, but you have no clue how you got there. And this is where the coroutines come into play, because they favor this story of a session rather than the sequential story. A coroutine implementation of the same echoing session would look like this, which is quite similar to the sequential code. So we allocate a buffer, perform a read, then perform a write, and then log. Except that we use this co-await, or generally co keywords, which turn our function into a coroutine, and all the magic happens. So you have a clear indication of the points where something will be suspended, some magic will happen. But before we go there, there is an even simpler thing to notice here. Previously, the session would return void. That is, it would return nothing, because we were just launching. There was no point in returning anything. Now we are returning something. In this case, it's this task of void. Task will be something when you are using a coroutine-enabled framework, is something that will come with a framework. So you don't have to pay a lot of attention to what it is. Somebody spent months figuring out the details and defining all the stuff in there, but you are just consuming it. You don't have to care about a lot of this. The point is that you are given a type. It will be a handle to a coroutine. This is how the outside world will be communicating with a coroutine. And you just need to use it. This is how coroutines work. The moment you put the magic keyword, you also need to use a special return type. There are many special return types. In this case, this is the one provided by your library. And another thing, interesting, you probably noticed, this function has a return type, but no return statement. This is how the coroutine favors our asynchronous path, but completely hides from us this regular synchronous path where we would return something to the caller. You cannot see it, but it's there. This is what the caller sees, whoever calls us. They see a function. They cannot tell it from a coroutine. Coroutine is something in the implementation. From the declaration, you don't know. It's just a function that you call. Only we know that this is a coroutine because we are writing the function body, and the compiler knows this because it also sees the function body. And what it does, it creates at least two things. It creates something that we call a ramp function. This is the function that the caller will actually be calling to get this handle. This ramp function will allocate a frame on a heap for a coroutine. We call it a coroutine frame, not surprisingly, where it would move the function parameters, that is the socket. It has to move it the same way as we had to move it in the previous example with lambdas, because this synchronous part, this ramp function, is very short. You call it, and you are done. The function parameters are gone, and the socket needs to remain somewhere. So we are copying. Actually, we are moving it. But conceptually, it's the same. We are moving to the safe place that will last as long as we need the coroutine to execute the last bit. So it will create, there will be a ramp function and the coroutine frame. And now the caller calls our session, our ramp function, passing in the socket, and the ramp function is executed. So it allocates the coroutine frame, and it returns immediately. So this is a very tiny operation. You get the handle back. And then at some point, our caller will decide to actually invoke a coroutine. And what is the interface for invoking the coroutine when you have this handle? And this is all up to the fantasy of whoever implements the coroutine type. They may choose to use function .run or a function call operator. Or in this case, someone used the coroutine interface for it. Because as with asynchronous computations, using coroutines is viral. So if you call a coroutine, you are also probably a coroutine, and there is coroutines everywhere. So co-await is a way of dealing with coroutines. We'll see in a moment how it works. And when this happens, when the caller actually decides to launch the coroutine, we go back to the coroutine frame where the socket is waiting for us, move also the coroutine body, and we can start executing the instructions, which will look something different than what we coded because there is a lot of magic behind the coroutines and secret functions and customization points being called. But this is not a part of this story. How the execution of this coroutine proceeds. We are now calling a different read. I called it co-read, but probably in your library it would be called something different. The point is this is another overload, different than read, different than async read, just some other read. And this function does nothing in terms of changing the state of the server. It's just an adapter. It adapts whatever interface our framework has so that it is an awaitable. So it just changes the type, changes the functions. It gives us an object that is an awaitable. And awaitable, in very short, is something that you can call operator co-await on. So let's do it. We call co-await on this magic object just returned. And our framework, hopefully it is implemented this way, records that we want a read to be performed to our buffer. So again, there will be no read at this point. It's just that the framework recorded that we are interested in the read. And it will perform it at some later point when it is convenient for it. And we also register a callback. But this time the callback looks completely different. Our coroutine at this point is suspended. So we will not execute the remaining part. will move out of the body of this coroutine and return, or rather pass the control to the system via this awaitable. And therefore the system can move on to doing other stuff, processing other sessions. The callback that we are registering this time is for the system to resume our coroutine when the read has finished. When the read has finished, it will resume our coroutine exactly after the co-await. So it will be there. The co-await operator will return something. In this case, it will be the number of bytes read from the client, and we can use this information to pass it down to another awaitable. There's another awaitable, so we are using the co-await and the coroutine interface to request a write. Again, not now, at some point later, and associate a callback. A callback will be that, again, we are suspending the coroutine, we are not executing it any further, and then the callback would be to execute at some later point this remaining part. So our graph here looks exactly the same as before. It's just that the way we expressed it in the code is different. And it's even more the same as the previous one because we have the very same memory management here. As we said, the coroutine initially will heap allocate a coroutine frame which will contain the state of the operation. It will have the socket here, there, the buffer, and they will live for as long as the last remaining bit of our coroutine needs to be executed. Except that this time, memory management is performed by the compiler and not by us. And this is better because we are not good at managing memory manually. Compiler will do it better. This is one. And two, it has an opportunity, even if it doesn't use this opportunity, to perform some optimizations there. And we are nearing the end of this presentation. This is how you write our session with coroutines for comparison, the previous code with lambdas, and it's not even complete because I wouldn't fit it in one slide. Looked like this. You don't have to use those lambdas. You can use regular automatic variables, and the normal lifetime scopes apply there. And this is a very simplistic example because we have performed one read and one write. Normally, eco server keeps reading and writing. So in the coroutine code is very simple. You just implement a while loop and you iterate as long as the socket is open. Try doing it with lambdas. It's doable, but then it is no fun. I mean, it is fun, but in different dimension. But you don't have to do some sort of recursion. In a read, you have to register a write. In a write, you have to register a read. I don't recommend doing that. I mean, you have to do that when you are not using coroutines and you are using this model of asynchronous computations. You need to report errors. We didn't talk about the errors, but the errors in this model are reported via exceptions. You call co-await. Anything when run with reading, the co-await returns with an exception that is thrown. You just catch it. With lambdas, you will have to do it manually with if statements. And remember to put it in every place. And that's it. The key point here and the beauty of the coroutines. You may have heard that the coroutine is a function that you can suspend and resume, and it's all true, but it doesn't reflect the heart of the coroutines. The heart of the coroutines, as I see it is a sequence of callbacks or those associations or of events with callbacks that you have, but it is reflected as one lexical scope, as a regular C++ code with all the C++ idioms. And note that coroutines are perfectly synchronous. At each point, I know what happens. I was able to explain what happens next. It's just they're a good synchronous tool for managing asynchrony. And that's it. If you want to play with it, Because I don't recommend, I mean, it's a cool, fun to implement your own coroutine type if you have time to do it. But usually you, in the future, which is actually the present day, you will just use coroutine types that your library provides. So if you want to play with it, not writing the coroutines, but just using them, I recommend, because this is the only asynchronous library that I've worked with, using Boost ASIO. It has a very nice model for asynchrony, and it offers a coroutine interface, if you like it. And recently, we have added to Boost also Boost Cobalt library, which is another and hopefully nicer coroutine interface for asynchronous computations. And that's it, what I've got. Thanks for listening.
Okay. Only one question we will have? That's good. That's good. Okay, so one question, Andrzej, for you.
You never know, it's one.
Thanks for the presentation. Do I understand correctly that the memory for the frame, for the stack frame, is allocated in heap automatically?
Correct. Even though you are told that in a simpler cases like generators, it can be elided, in this case, when this is a proper coroutine for asynchronous tasks, for sure you will get a heap allocation.
Can I override it somehow to use a pool or my custom allocator?
You can provide a custom allocator via this. It wouldn't be you, it would be somebody who is defining this task of void.
Yeah, but it's technically possible. Let's say I'm writing the coroutine, this coroutine system. So
yes,
I can configure it to use not heap, but something else.
Yeah, you could provide an allocator, an equivalent of function new and delete.
Mm-hmm. Great, thank you.
We have another question. It's
Okay,
like one question
good.
triggers another.
Let's go for it.
On the other side,
Over there.
right in front of me.
Franz. Okay, thank you a lot for your presentation. I was impressed that C++ becomes kind of similar to C# in some ways. Your presentation was focused mostly on asynchronous network input-output. As far as I'm aware, Linux recently added the file asynchronous IO. What do you think that there are a chance for some other possibilities? I'm still surprised that's not something like that for DMA, like when you need do mem copy, then you just block the entire thread. So I don't know if there's readily available alternatives or maybe some other uses for this approach.
I'm pretty sure that at some point you will get a similar coroutine interface for doing file I/O, asynchronous file I/O. The history, because I didn't tell it, but actually when I'm presenting this, I mean Boost ASIO library behind the back. And the order of things in Boost ASIO is that they wanted to do I/O, they concluded that it has to be asynchronous, and now they concluded it needs coroutines. The same would be with asynchronous file I/O. You know, efficient file operations need to be asynchronous. You will need a coroutine interface or some other interface for convenience, for doing this conveniently. So yeah, I would expect libraries like this to show up for file I/O.
What about direct memory access like memcopy or something like that? I think more about totally different domains, mediums of where data can be transferred to or from.
And the question is if the same coroutines can be, this is how I understand your question, if the same thing can be used for anything asynchronous, not necessarily file or memory, just any asynchronous thing.
Yes.
Yes, this library mixes the two, but conceptually there are two separate things. You can provide this a coroutine interface for doing any asynchronous thing.
Thank you.
Okay, thank you very much. Thank you, Andrzej.
So thank you again.
Okay, thank you.